be sharing, and you should now also be able to see my slides. Unless somebody,
yeah,
perfect.
Looks great.
Okay, well, hi, my name is Stoop, but maybe first, who am I? I'm a PhD at Utrecht University, and I'm interested in critical events, specifically those caused by climate change. And currently I have a focus therein on the energy systems and how they interact. My personal background is also from climate physics, but I'm currently working in the overlap between the fields of like data science, climate science, and energy science. And I'm in a project co-working with with the Dutch TSO, also there to work on my personal focus a bit, to align the methods that are used in industry and industrial applications with those that are used in academics, because we have a lot of interesting insights in our work that can be used either as checks and balances for the reports published by TSOs or for cross-pollination of the methods used. And today I will share a bit on the work, ongoing work on this topic. This work is part of the ACDC ESM project, and I'll first quickly introduce that. The ACDC ESM project is on algorithmic computing and data mining for climate integrated energy system models, a whole mouthful. And two PhDs are working on this. Rogier and I, we are trying to do integration of computer science into these energy system models. Rogier works mostly on the algorithms and trying to improve the algorithms of energy system models, and I work on data mining methods that can help us to integrate the climate data into these models. This is a cooperation between energy and computing sciences, and we are working together with the Dutch TSO Tennet. And we want to find the influence of renewables, storage, and demand response on the adequacy of the European energy system. To give some background. Then, okay, as a climate scientist, I might want to say, okay, what are the impacts of the weather on the energy system? And we then might look at, we take a relatively simple or a relatively simple in the energy system perspective model, where we take some meteorological variables, we take some societal variables, we combine that using some impact functions, and then we get some outputs of energy variables, for instance, energy production from wind and solar, and a metric to also get the energy demand, and we can combine that in energy shortfall. And based on this value of energy shortfall that we then have, either for a country, for a whole region, or for only a small grid box, we can then look at extreme characteristics and determine the timing and the risk of an extreme event, whatever such an event might be. This I've done together with Karen van der Wiel, and we found that if you look at a very large data set that she had created, that the most extreme events are caused by these high pressure systems over Central Europe in the winter. These traditional Dunkelflaute systems, as they're called in German, or wind cold droughts in the middle of the winter. And what you see there is that those events are happening in the middle of the winter. And if you look at an event that is not very short, but even if it's longer, you see that these events are January, February based, and they are generally associated with extremely cold weather over Central Europe due to this high pressure system that does a lot of radiative cooling. So then we were wondering, like, hey, these events are in winter. And in winter, we can characterize the weather. We can characterize weather based on weather regimes. And these weather regimes can be used as an indication for the large scale circulation. And what you can then do is you can define, for instance, you define 4 regimes, or you use 4 regimes, and you can give them a specific use or name. And then finding these regimes, you can see that there's like the now positive, the now negative, and the Scandinavian blocking and the Atlantic ridge. And each of these regimes has their own characteristics also on the system. And then if you look at the risk, and here we look at the normalized mean of the risk. So, hey, is there more or less risk under such a system, such a regime? We find that for energy production, we see that there's a higher risk under now positive. Higher generation under now positive, so lower risk, but now negative, and Scandinavian blocking have a lot of less generation. And for energy demand, the signal is less strong. But then if you combine them in energy shortfall, we see that there's a very large risk for Scandinavian blocking events that have like very limited generation, but also some increase in demand. So this might be an issue to work with. And then, okay, given that you have these weather regimes, what does then the explicit generation look like? For these weather regimes, we see for this Scandinavian blocking, we see that there is reduced potential in the generation from wind and energy potential in Northwest Europe over the North Sea area, while at the same time there is slightly increased potential for solar energy. But due to the extremely high demand, due to the cold in Europe at those points, you see that this is an extremely difficult point to work with. And this was seen both in the ERA 5 dataset, so reanalysis, as in high waves. So these regimes can be used to somehow quantify the risk based on a simple impact model for climate. But what if we take a different approach? What if we say, okay, we don't want a simple impact model, we want to actually represent the grid. So what we've done is, together with Rogier, we run an energy system model for the TYNDP scenarios. These are the scenarios from the 10-year network development plan in Europe. And these have different assumptions on how the European network is going to develop over the next years. Either a very distributed system with everything shared. There's a national trend, which is a very localized system. And there's a global ambitions where there's a lot of cooperation, a lot of trade, and also a lot of increase in transmission capacity. And then in this model, we represent the full European Union with transmission between the different zones, market zones. And then we want to look at system reliability and adequacy to assess, okay, how does that work? And to assess this reliability, we first look at the timing of the system limits. We can see, okay, this connection between regions allows for additional transport. So that allows for a certain transport limit beyond the normal thermal limit you have from your thermal generation units. Additionally, you can also have some storage in your system that allows for some storage and temporal shifting of your demand from certain points in time. Hey, if you have a peak demand in the evening, you can store energy for that for later, or you can use that storage at that point in time. And then if you add these limits, the thermal limit from your base load, from your thermal generators, the temporal limit and your spatial limit together, you get the actual limit of the system on when there's no longer possible to meet the demand that we have. And then you get, for instance, for a scenario like the distributed energy 2040 scenario, you get information like this, like for every week in the year, we get information and we see, okay, most of the time, there's no issue under this system development. But for some countries and some points in time, for instance, the winter period, we see that there is more times or more instances of unserved energy. So what we did is then, okay, can we look at that a bit more? Because again, these events are in the winter. So, but before we wanted to look at it again, we wanted to say, okay, now we've looked at just an instance. At this point in time, there is some loss. There is some loss of energy. We don't know how much. That might not be the best metric, because the loss of energy or the loss of load expected is an arbitrary unit that is 0 or 1. You have loss of load or you don't have loss of load. And a better metric to look at or use might be to use energy not served. So what we do is we run our energy system model under cost assumption with constraints on transmission. And then we added additional constraint after we have the cost of our system, and we try to either minimize or maximize the loss of load expected for the same unserved energy. And what we find is that for a system where you maximize the loss of load expected, you see that the system just spreads out the required energy over a very large region. So it spreads out the point of failure from one zone to all the other zones. And that is not always what you want. So here, if you maximize the loss of load, you have just a lot of countries that have a bit of loss of load, but the actual energy that they miss is only small. Well, if you minimize the loss of load, you see, okay, actually the issue is in Sweden, in the third Sweden region for this model iteration. So what we in the end started to use is we want to use these energy not served, because this gives a better indication while minimizing the loss of load. So we want to say, okay, we want to minimize the number of regions under consideration that have an issue. Where is the actual issue in our system? And then we say, okay, what are the timing of the events then? So we don't use the loss of load expected. Now, okay, quick backup. We have these high impact events, and they're generally during the extended winter period. So there's the shortfall in this simple climate impact model, and there's this energy not served in the full energy system model that we get. And both are found in the winter or the extended winter period if you take the months around the winter. And in wintertime, weather regimes are generally a nice method to classify the weather. You can use 4 regimes, you can use 7 regimes like Christian Grams used, or you can use 6 regimes. And Valkena et al. Have given a very nice consideration why 6 regimes is the optimal to use. Because if you use 6 regimes, what you get is that there is a very nice balance in symmetry between explainability of, okay, what is the regime, how does it look like, and also on the coverage, because the more regimes you use, the more points in time are covered. You use also the bit more odd one out points, but the less regimes you use, the more explainable they are. And what they showed is that if you use 6, you have this nice balance between a positive and negative phase for both the Atlantic Ridge, the Scandinavian blocking, and the North Atlantic Oscillation, and that they explain for the wintertime all points in time, instead of that you have this undefined weather regime state. So we use this, and then we run that over our whole model, and we get a lot of data out of that. And then you're like, okay, what do we actually see? Because this is a lot. And then we see that our results, when you explicitly link this unserved energy to these weather regimes, and then you see, okay, you classify it per weather regime, and you see, okay, how much energy not served do we have? You see that it depends on the scenario. For some countries, for instance, do we have here Slovenia, Slovakia, you see that they are very strongly dependent on this national trends scenario. While for others, like Turkey and Romania, you see that they are very dependent on this distributed energy scenario. At the same time, we also see difference between countries. For instance, in Norway and Sweden, we see a relatively even distribution over all regimes for the amount of energy not served that we find. While for other countries, actually for most countries, we see that there is some peaking under Scandinavian blocking in positive phase. At the same time, we also see we have 55 market zones, but there's only 35 market zones that actually have, at some point in time, unserved energy. So 20 market zones never actually see a point in time with an issue under these system design specifics. So then we aggregate this a bit, and we look, okay, we don't want to look at the difference between all the countries, but we look at the difference from over all the regions. And what we then more clearly see is, for most countries, we see that there is quite a high peaking for for quite a few scenarios where you have this issue under the Scandinavian blocking plus, especially under the national trends assumption, which is roughly how current policies on the deployment of renewables are. Also very strongly on the distributed energy system, where you have everything distributed on a local level. You try to solve everything locally first before you take up energy from the network. But in the global ambitious scenario, we don't see this as strong. We see that there is quite some spread between what weather regime increases the risk. Here I've stacked, which is a bit not maybe the neatest way of doing this, but here we've stacked for each market node this unserved energy to a total over the different events. And then you can more clearly see this behavior that for the distributed energy and for the national trends, that there's a strong dependence on the Scandinavian blocking plus, and also a reduced risk under this now negative state, which is also nice to know, because then you know, okay, hey, if a Scandinavian blocking might be followed by now negative, we might be able to use some shifting or some longer temporal shift in demand to solve our problem. So in general, the key points I wanted to give away is that weather regimes can be used as an indicator for risk. We saw an increase in risk under most scenarios for Scandinavian blocking plus, and a reduced amount of risk for the North Atlantic Oscillation in a negative state. And these weather regimes are very well defined in the winter period. However, the definition we used here, based on the work by Falkner et al., is not very accurate in summer. So if you would want to use this method to also represent weather regimes in the summer, you could better probably use the method presented by Christian Grams, because they use 7 different regimes and include a regime of, well, basically a known defined regime, and that way you can better accurately indicate this risk. We found that there is a link between these weather regimes and this and the energy system that is very much dependent on the scenario. There's a different risk under global ambitions than under national trends for distributed energy, and that there's differences between regions. The Nordics in generally have a very flat dependency on, independent of these weather regimes, on the amount of risk that they see. And it also depends a bit, I've not shown that here, but I can tell you that the energy system model, the amount of detail that you put into this energy system model also reflects the amount of moments you have of unserved energy. In general, our work here only worked using historical climate data. So climate change and climate change effects on the amount and the occurrence of weather regimes is not taken into account. And with that, I would like to round off. And if you have any questions, please already type them in the chat, preferably on the Slack chat, and I'll hand it over to Justin.